models, and you could use that for machine translation. And the idea here, le chien sur la plage, the dog on the beach. So you want to translate French to English. And so you could imagine learning end-to-end, and I will tell you in a second what end-to-end means, what it means in this case. But you can learn to encode the chien. But right now, I didn't define the loss. So just that is, you can't train that easily, although you could maybe in an unsupervised way. But the way many people will do, at least was done for a while, is to do it in a sequence-to-sequence model, or what's also called encoder, and then this is the decoder. So encode the sentence and then decode the sentence. And so you encode in one language, you get this intermediate representation, and that intermediate representation then is added to a language model. That language model could have been trained in another language, another corpus. So you could have trained in another corpus to generate language given an input. And you could have also in your first language learned to generate a representation. And then you could imagine, so you have an encoder trained on French, you have a decoder trained on English, and you could imagine training a third neural network that will translate from one language to another language. And that is training each module one by one. This is in contrast with what's called end-to-end training. End-to-end training says, I will train everything, my encoder, my translator, and my decoder, all of it, I will train it end-to-end. And so my loss is going to come really late in the process, because the loss is going to come very late after the whole translation. This is what will need to go back and all the way. So the gradient coming here has come all the way from here or from all of them. So what is the loss function? I kind of hinted at it. The loss function is so here I made a prediction of what the word should be, or in reality is often a distribution of those over those different predicted words, and I can see how well does it match with the ground truth. And then if it does, I can, that's one part, that's one term of my loss. I have another term of my loss, and then you just sum over them. So the loss is only defined in your second language, in English. Only the English sentence is used here. The French sentence is only used for the encoding. Okay, this is examples of RNN, but RNN, and that was well discussed in the 1990s, has one issue. Recurrent neural network, typical recurrent neural network, has one well-documented issue. There's beautiful papers on this topic, that the gradient is vanishing over iterations or over layers. And that issue, I hinted at it also, and I think someone even asked a question, I think maybe, or at least I know I mentioned it for convolution neural network, very, very high number of layers in a convolution neural network. The by default convolution neural network past 10-ish layers will have a trouble also, meaning that the loss will be propagated through the gradient, but will be attenuated and eventually vanishing, or the opposite, sometimes it will blow up. And these happen primarily when the weights are tied, although it will happen in different situations, but it's reinforced even more when the weights are tied between layers. And you can see it in the RNN. If the RNN is, you have the same weight, because the RNN at time t plus t, at time 1, time 2, time 3, time 4, the same weight W is the same weight. It's the same weight here, the same weight here. So the influence of a given input on the hidden layer, and therefore the network output, either decays or blows up exponentially as the cycle around the network recurrent connection. So if the W for one specific type of activation gets very high, and you do it over and over and over, then you have this multiplication over W. And so if you multiply it many times, then it can either decay or blow one or the other, either one not being great for the gradient. And so the gradient, the impact on the gradient will be much lower. So this is the issue of this. And so for that, there has been different approaches, all inspired by often with like, the idea is to shortcut this as much as possible. And if you remember in a kind of convolution neural network, the ResNet, there were those skip connections, and they were very important to help that. The GRU, which I may not have slides about it, is an example also where it has a little bit of almost that skip connection. It's not exactly that, but it's almost. But the one that was very popular. What's interesting, it didn't get popular when it got first proposed, but then got very popular when the deep neural representation increased in popularities, and it's a long short-term LSTM. And so I want to just draw like what a typical RNN. This is just typical RNN. So this is an input. I have one layer, neural representation, neural network, and then my score. And this is repeated over time. And so I'm showing this link between HT and HT minus 1. And the typical way will be multiplied by W, and then with some kind of activation function. And then that will be giving me the impact on HT minus and HT plus 1. So this is just the same equation and if you remember, HT plus 1 will also have the evidence of XT plus 1 added to it. So this is just the typical RNN. Now, the idea here is to have a loop, a memory to kind of shortcut things. And the idea here is I will have a new variable, a cell, a memory cell, that will be there to shortcut it from time t to t plus 1. And this one will have its own self loop. And so, so at the memory at t minus 1 will be used for as an impact on the memory at time t. And so this is sometimes called the forget gate or the memory gate. That's the net terminology. And then what happened is the following, is that I will use a sigmoid function. And if you remember, the tan H is great because it gives me from -1 to +1. But the sigmoid is a beautiful gate function because it's either 0 or it's either 1, and it quickly goes, and it's not too sharp that I can't have a gradient. So what I will do is I will put a gate there, and the gate, what it does is says how much should I, from these evidence that I gathered today, right now, from these evidence that I gather at time t, which one should I keep? And I'm going to use, look at this and decide if I should keep this input. And then I will also use my same information to decide if I should use it from time t plus 1. If you have to remove one of the gate, the output gate is probably the one to remove that has the least impact, but the LSTM has this output gate. And then what I have also is another one which is called the forget gate that says how much of it from the previous memory. So I have an LSTM cell And I have one also for between t-1 and t that is here. And so there's a shortcut between the cell memory here that goes into, that's what is shown here, and that goes and then is multiplied by the gating that says, hey, how much should I remember from the previous time? And so my shortcut, I have the possibility with this gate to shortcut always. And so from a gradient perspective, that can also help into that. And so this is the compact way to write this, where these different gates are in fact just different function, all using the same input and having this large W that's related to that. And there's a little bit on the notation. So this is the idea for LSTM, and the main key to remember, the main two important one, the input gate saying, hey, how much of the current evidence should I keep accumulating over time? And the second one, how much of the past like that so this is about current evidence. This is about past evidence and how much I put them together. And then the output is how much should I use it in the future. A little bit less important. So these two are very interesting. The GRU is an extension that tries to do with fewer number of gates into that. So the gradient can still be computed. In this case, the link between h at time t and h at time t plus 1 will be, instead of a direct activation like neural layer, one layer as we had in a recurrent neural network was just a one layer neural network here. Instead of that, then you have the LSTM. But because you can compute the gradient internally, this is all, there's a gradient that can be computed from the output to the input. Because there is that, then you can also go and compute an LSTM. So this is an LSTM shown with the loss. And if you remember the loss, if you have a loss at every point, then you just sum the loss, or if you have a loss only at the end. If you remember, one of the issues of recurrent neural network is that they are directional. So you can, one thing you can do, whoops, sorry, wrong way, is to go bidirectional. So you take one input, one LSTM one way and LSTM the other way. And how do you take both input together? Think about it for a second. How do you take both inputs together? The idea here is to concatenate them. You just concatenate them. And so if your LSTM here give you a H output of size, let's say 200, and this one give you an output of 200, then the input for Z will be 400, and then you will have your, I don't know, softmax or something to get your scores from that. Or one more layer on top of the LSTM. There was a popular, it was very popular for a very short amount of time. It was Elmo. It got very popular for a very short amount of time. And this one was like, hey, we love word2vec, but there's all these ambiguity with words like plant. And it seems that if you knew all the other words around it, it will work better. So the idea is, let's do maybe possibly just something like word2vec at each of these step, although it's not necessary, but let's say for now, for the purpose, is that let's say that each word has its own representation. And then I'm going to use an LSTM to encode how much influence the other words have on each of the words. So if I have a word plant here, and I can go and look at the word before, and if the word before was green, then green plant is likely means that the meaning of the plant, and so the output here of the meaning of the plant will be, the output here will be a meaning that's a lot closer to the flower plant instead of the factory plant. So the input was the same plant here, but if it has been industrial plant, then in this case, the output here will have been different. So the Elmo does it. You could also have it does it in bidirectional and 2 layers on top of that. This is, and you can do it over multiple, I said, you can do bidirectional. You can do bidirectional and multiple layers of bidirectional. Elmo had 2 of them. And coming soon, there's a lot more to talk about for sentence representations. And I love this topic. This is great. And there's a lot to talk about, self-attentions, but we'll talk more. But to talk about these, it's important to talk about alignment and attention models. So they will come in about 2 weeks from now on this. You can read about it if you want in the meantime, but we'll discuss more. The last part of the lecture today will be about syntax and how do you represent language, but go beyond just the meaning of a sentence or meaning of a word, but also look at the syntax and the structure of the language, which can also have an impact on the meaning, but can by itself be some useful information. So I have a sentence, and the sentence, simple sentence, Alice ate yellow squash. Very simple. What can you tell me about this sentence? On one side, you could tell me something on the meaning of each word. Alice is the name of a person. Ate is an action yellow is a color. Squash is a vegetable. So there's a meaning, and there's a meaning of the whole sentence, a meaning of someone doing an action of eating a vegetable. So there's a meaning. That's all we talked about earlier. But there's also, from that same sentence, there's more to it that you can look at. There's the part of speech of this that you can look at. So Alice is a noun, ate is a verb, yellow is an adjective, and here we have a noun. So this is part of speech tag. This is telling me about the role of a little bit, you could see as almost the syntactic role almost of the word. And then there's also what's really, and that's takes a little bit of while, but that's a very important and useful concept. The concept of noun phrases is very useful. And I found that if I look at language now these days, people look at it at the sentence level, and then they will do birth or something at the sentence level. But there's a lot to gain if you look at it not at the whole sentence, but look at a little bit at parts of it. And I will say noun phrases are a very useful granularity of analysis for words, for sentences. And so noun phrases means it's in this case will take also it's not just a squash, it's a yellow squash. It's referring to the same entity. So noun phrases is important. There's something called verb phrases, which is where take also into consideration the verb and its complement. And then you have another noun phrases and then a sentence. So this step of like taking a sentence and splitting with noun phrases and verb phrases, this is what is called syntactic parse tree. Syntactic parse tree, or if you just use, there's also another simplification of that, which is called chunking. Shallow chunking. Shallow chunking, which is like finding which all the noun phrases in it and all of the verb phrases. You're looking at the sentence and like just chunking it into this. But the more like systematic way is to look at it not just as a clustering of words that are close to each other, but seeing it more as a tree structure. So that's very useful. I think noun phrases are useful. They're a lot more meaningful in itself. If I had to do an attention, like attending certain part, it will make sense to not attend just on the squash, but to attend on the yellow squash. This will be a lot more meaningful than just attending on the word squash. So this is what a syntactic parse tree would look like, or can look like. But there's another type of syntax structure that is really useful. And this one is the fact is named dependency grammar. And that one is useful because it also suddenly gives you pairwise information. Like it's like, in this case, the Alice is the subject of the verb ate, or the other way to say it, what is the subject of the word ate? The subject of the word ate is Alice. What is the object of the word the object of the word ate? And it's squash. And what is the attribute? And so this dependency is really useful because ate, the person did not eat yellow. The person ate the squash, and the squash is yellow. So that is another type of structure that's interesting. This is a very simple example, but there's some a lot more complex than that, as you can imagine. If you have longer sentences, there's a lot of ambiguity in this, but dependency is a useful thing. And one aspect of dependency also that's interesting is the root of this, because we often think of language and the beginning of a sentence being the first word, but often that first word is probably the least informative word. If it's a determinant, it may be one of the least informative of the whole sentence. So the root could be quite a lot, very informative. So main idea is the syntactic structure consists of lexical items linked by binary asymmetric relation that we call dependence. That's more general. And it's easier, there's something about, this is by default a tree structure, but you could also look at it as a sequence modeling problem, but this is not a one-to-one mapping. So there's a little bit of problem into that. One of the issue with syntax, it's sometimes ambiguous. So the word like, the verb like, the word like, it can be a verb or a preposition. I like candy, time flying like an arrow. So in one case it's a verb, in the case it's a preposition. So if you do part of speech tags and say, oh, every time I see like, it's a verb. No, you need to look at the words before and after to be able. The word around can be a preposition, a particle, or an adverb. I bought at the shop around in the corner. I never got around. A new Prius cost around. All of this are different syntactic. So language ambiguity is a classic. In fact, that's one of the reasons we see so many papers in natural language processing. There's ambiguity syntactically, which I'm emphasizing here. And there's also ambiguity semantically, as we talk about for the word plant. So the sentence like salesman sold the dog biscuits. You could imagine they're very different version. In fact, if the capital B, you could say biscuit is maybe the name of it, although it will be unusual to see a S to the name. You could think that the salesman sold the dog biscuits. So it sold dog biscuits. So the type that was sold is biscuit, and the attribute is dog. Or, which is only a bit unusual, but your salesman sold the dog biscuits. So it's hard to sell dogs, to sell to a dog, but for the purpose of this example, you could imagine. So as a summary, there's many examples for pattern of speech tagging, constituent on constituency parsing or dependency parsing. And so for a lot of them, a simple sequence modeling may not be sufficient. And so the question that you will have, and I just need a few more minutes in this lecture, is like how to take advantage of syntax and tree structure within a neural network. And there's one example for that. There are a few more, but I want to focus on today are recursive neural networks as a way to do that. And so how to model syntax with RNN. And so, because that's one of the way you could imagine doing it. And so you could decide that although we know that syntax is a lot more complex and there's a lot more information, you could say, hey, I'm just going to model part of speech tags. And then I can use an RNN. But the other option is to use what's called tree-based RNN or recursive neural network. And these are really cool. I'm missing an arrow here. But what the beauty of here is in the same way that in a recurrent neural network, the weights are tied, meaning the weights here are the same as the weights here, are the same as weights here. In a tree-based structure, the same idea will come in. So you will say, give this structure, this module, this what's called a unit. This unit is designed to take 2 inputs and output one output. It takes 2 input and takes 1 output. But the weights here that are learned and the weights that are learned here, the weights that are learned here, weights, all of these will all be the same. They will all be tied together. Now, one thing you're probably asking yourself is, how do I know that the word the should be connected to this and not the word likes? Like, how do I know the tree structure? And the answer is, it's supposed that I already beforehand ran the syntax parsing software, and I will use this information to inform the tree structure. Because my goal here is maybe to do, for example, maybe I want to do sentiment. So my goal is to detect sentiment. That's what I want to do. And I could do sentiment by just doing a recurrent neural network. But here, I want to take advantage of all of this syntactic information. So what I will do is step 1, get the syntactic information like a dependency tree, or here what I see, looking at noun phrases and verb phrases information. And so use this kind of parse tree. This is not a dependency tree, but this is a parse tree, and use that to create my structure. And then I will use a tree-based RNN to learn how to aggregate 2 input to make 1. And the beauty of it is, for every sentence, I have a different tree, because for every sentence, I will have a different representation. And so I can go ahead and for each of them, but this is the same as an RNN. In an RNN, I can have different length, and that doesn't matter as long as I know the length, or I have a magic stop token to tell me when to stop. But the other way will be just to know what the length is. And so if air, it's a little bit like the same idea. As long as you know the parse tree, then you can have a different tree structure. The recursive, the unit, like what does it look? It looks as the same as a typical neural network. It's just that you concatenate the 2 inputs. So I have the boy, and I just concatenate whatever representation I had for the and the boy, the word boy, and just concatenate. Maybe I have word to vec, and then break these 2 together, and this gives me my output. The output will be designed to be the same size as the output that I had here, so that I can go and have the this hierarchically. And so I can use it to do sentiment analysis, and that was state of the art for quite some time. And what's nice is I can get two things for it. I could have one loss that is only at the end that says go for it and go all the way, and I can get a loss all the way at the end. Or I can go, and it takes a lot of time to annotate it, but I could imagine annotating sentiment for every element in my tree. So very, is it positive or negative? Good. Is it positive or negative? Very good together. Is it positive? And then not very good, and then that becomes negative. So you can you could imagine, and that was that sentiment tree bank was a lot of work for this, creating that. So and that recursive can be used for sentiment analysis. Once it's trained this way, it can give you for the whole sentence, or for a specific noun phrase, it can give you all of this information. I want to show you one last, which is called Stack LSTM. I really like that one. I'm not going into as much detail because of time, but the idea is as you do parsing, when you do parsing, one of the older way to do parsing is to do it because it's a tree. These parsers, like the syntactic parsers, and one of the good way to do it was to do it with a stack. That's the way it was done, and that can be very efficient. But how do you do a stack with a recurrent neural network? That has been a question for a while, and there was this nice paper from Chris Dyer about stack. And so the idea here is that you have the stack of partial constructed dependency tree. You will have also a buffer of the words, and you will have a stack also of the current word. And the idea is that the stack will be implemented in practice the way a stack. So this is not an LSTM. This is not a stack LSTM. Sorry, the header should have been. This is just the typical way that you can do parsing with. But how can you implement that with stack LSTM? The idea is that you parse your sentence, and then if you find a moment where you should have pop, then suddenly what you end up doing is putting this information in a second stack, and then you continue, and then you're going to link from an LSTM. So it's almost like a recurrent LSTM. It's just that at the end of the day, I add this extra link, and these extra link in practice will be implementing the stack LSTM. And so I invite you to look more in details to that. And these are some of the parser softwares that exist. Some are a little bit older, but these are some of the links from that. So thank you very much for your attention.